All right, let's do a few more practice problems with the work energy theorem. So I have an 8 kilogram box that rests on a rough floor. So let's put it here, 8 kilograms, rough floor, so there's friction. The coefficient of friction is 0.5, mu equals 0.5. And I want to know what is the work needed to move the box at a constant speed. Constant speed means the acceleration is 0, means we are at equilibrium, means that the forces will cancel. Okay, so this is part A. We'll do part B over here on the side. So the idea is if you're moving with a constant speed and there's friction, let's say you're going to the right, so friction will be to the left, which means that you're pulling to the right this way. Friction kinetic. Constant speed means that these two guys have the same magnitude. Okay, and obviously here mg and normal. Now you might be wondering, if they have the same magnitude, then maybe this box wouldn't move at all. Well, the idea is that at some point the box was already moving, and now it just continues to move at a constant speed. So we don't argue with how we got to where we are or what happened earlier. We just go with what we're given, right? So these two forces have to be the same, and it's asking what is the work needed to move at a constant speed. Constant speed, according to the work energy theorem, if your speed is constant, remember, your delta K is 0 and your work net is 0. So you might be thinking the work needed to move is 0, but it's not. What this question is asking is what is the work done by F, okay? What is the work done by the force? Now it's a little tricky because in other problems, I told you that if I'm asking for the work done, the work needed for something to happen, but I didn't specify which force, you could assume that it was the net force. And that's because in those problems, we didn't know exactly how many forces there were. So even if there was a force going against you, you just think of the whole thing at once. Well, as you move to the right, a distance of 3 meters, friction is doing negative work against you. But the net work has to be 0, which means you have to do the same amount of work, except positive, as friction is doing negative work, so that those two cancel, okay? So what this question is asking is what is the work done by F so that you're able to accomplish constant speed, okay? I have no way of finding F if not through friction. So I have to calculate friction to know what my F has to be. And that's because to find work done by F, I'm going to need to know what F is because it's FD cosine of theta. F goes this way, delta X goes this way, so the angle is 0, and the distance is 3. The cosine of 0 is just 1. But I do need to know the force, and that force will be friction. Force is friction kinetic. Friction is mu normal, or mu normal cancels with mg. So mu is 0.5. The mass is 8, and for gravity we're going to use 10, which makes this force 40, and that's exactly what goes here. So the work done by F to get this moving is 120 joules, which also means that the work done by friction was 120 joules, but in the opposite direction, okay? So here we wanted the work done by F to cancel out friction so that you move with a constant speed. Now we're moving with a constant speed 3 meters in the vertical. So if we're moving in the vertical, it's because I'm pulling this way. And I'm going to call this F as well. Force going against here is mg. Now there is a normal while it touches, but as soon as it leaves the surface, there's no longer a normal. Okay? And that's where the problem starts, when it just leaves the surface, and it's going to move up with the distance. This is usually d, but I can call it h, whatever. I'm just going to use d to stay consistent with the other equations. Or I guess we'll call it both. d and h equals 3 meters. Okay? Now, how do I move with a constant speed? It's very similar to here. Here, for me to have a constant speed, my f had to equal my fk. In the very beginning, it was a little bit more to get it moving to overcome static friction, but then I pulled with less force and I kept a constant force that's the same so that they cancel. Same thing here. To get off the ground, you have to pull with a little bit harder than mg, but as soon as you pulled a little bit harder than mg and it gets off the ground, your force will be the same as mg, and that's so that your acceleration is 0, and so you move with a constant speed. Okay, and if I want to figure that out, I can say the work done by F is force d cosine of theta. Here the force is this way, the displacement is this way. These two guys are parallel to each other, so the angle is 0. And the force that I need is mg. Okay, the force is mg. And I'm going to call it, instead of d, I'm going to call this h. And the work needed is mgh, which should make a lot of sense. This is the potential energy. You're giving this thing potential energy. Another way that you could have thought about this is the work done by F is the work to lift. You might remember that the work to lift is mg delta h. Now h here is 0, so this h here implies h means h final. So these two guys here are in this case the same exact thing. Okay, so those are the two ways you could have done this. The force is, let's just plug in from this equation here. So m is 8, gravity is 10, and the height is 3. So the answer is 240 joules of energy. What you might see real quick is that it takes more energy to lift this than it takes to move it horizontally. Okay, and that's always going to be the case. Let's keep going.